Okay, so today we're going to be using second derivatives. So hit pause, get a lesson objective down. When you're ready, hit play, and we'll look at these functions then. Okay, so we're going to be looking at concave and convex functions. A concave function looks like that. If you look at its gradient is decreasing over the interval, and it's got a line segment that joins below the function. Okay, so it's got a decreasing gradient and the line segment is below the function. That's our concave. A convex function is the opposite. Its line segment is above the function and its gradient is decreasing over the interval. And some functions have got both convex and concave sections in them. There's our convex and concave. So we might be asked to find the interval over which it's convex or concave. So before you make some notes, I remember concave, just something that might help you remember. Concave is like a cave because you can take shelter in a cave. So that's how I remember concave function. Hit pause, make some notes on these. When you're ready, hit play and we'll look at each of these in turn. Okay, so let's have a look at a concave function. There's our concave function with its gradient that's decreasing and the line segment that's below the curve or below the function. It's got a decreasing gradient, so we can say that the rate of change of the gradient is negative, and we can say that its second derivative is less than or equal to 0. So two important points to note: it's a decreasing gradient and the second derivative is less than or equal to 0. So hit pause, make some notes. I think those two are the bits you really want to write down. You can write about the rate of change being negative. Once you're done, hit play and we'll look at a convex function. Right, so where our concave function had a decreasing gradient, our convex function, alternately, has an increasing gradient over the interval. Okay, so the rate of change of the gradient is positive, and the second derivative is greater than or equal to 0 for all values of x. So again, hit pause, make some notes. When you're ready, hit play, and we'll look at an example. Okay, so let's have a look at this example here. It says for the interval on which find the interval even on which the function x cubed plus 4x plus 3 is concave. So our function is given by x cubed plus 4x plus 3. So our first derivative or gradient is equal to 3x squared plus 4. Now we need to look for that second derivative, d2y over dx squared. That's going to be equal to 6x. Now, for a concave function, the second derivative has got to be less than or equal to 0. So for a concave function, terrible handwriting, d2y over dx squared, it's got to be less than or equal to 0. So that implies then that 6x must be less than or equal to 0. And if we divide by 6, that means that x is going to be less than or equal to 0 for our concave function. So hit pause, copy the example down. When you're done, hit play and we'll look at another example. Actually, before we look at another example, let's have a sketch of what x cubed plus 4x plus 3 looks like. And that's our function, and from 0 onwards it's a concave function. Sorry, for less than 0, so below 0, not onwards, less than 0. There's our concave function, and there's our line segment below the function. Okay, so you can sketch that curve, and now we look at another example. Right, in this example it says, show that the function f of x equals e to the power of 2x plus x squared is convex for all real values of x. So we've got our function e to the power of 2x plus x squared. So we've got to differentiate it in the first instance, f dash of x, that gives us 2e to the power of 2x plus 2x, and then we differentiate it again, f double dash of x, which is equal to 4e to the power of 2x plus 2. Okay, so we know certain things about the exponential function. We know that e to the power of x is always going to be greater than 0. We can sketch it here quickly. It approaches the x-axis, it takes off then, so y equals e to the power of x. It's y and that's x. So it's always greater than 0, that's 1 where it intersects its intercept. So it'll be the same for e to the power of 2x, that's also greater than 0. If we multiply it by 4, we're stretching it in the y direction, so 4e to the power of 2x is also greater than 0. It's a stretch, it becomes steeper. But when we add 2, then we're shifting it along the x-axis. So 4e to the power of 2x plus 2 is greater than 2. So this function is always going to be bigger than 4e to the power of 2x plus 2 is always greater than 0, which means that f dash of x is always, f double dash of x is always greater than or equal to 0 for all values of x. Therefore it's a convex function. So we have to prove it in a slightly different way. Hit pause, copy the example down. Once you've done that, hit play, and we'll move on. Okay, so we spoke earlier about functions which contain both concave and convex sections, as this one does. So we've got a concave section here and then changes to a convex section. So there's a change from concave to convex, and it's got to be at a specific point. So there's our concave function. See the line segments below the function. I was about to say below the cave, but there's concave there. At some point it switches, and then it becomes a convex function then. Okay. Where it changes is known as the point of inflection. So there's an exact point when it changes. That's the point of inflection. Now the point of inflection, what do we think the second derivative is equal to? The second derivative is equal to 0 at the point of inflection. I prefer this spelling. Okay, so hit pause, make some notes. When you're ready, hit play, and we'll look at an example. So we got this curve here, x cubed minus 2x squared plus 4x plus 5, obviously a cubic with intercept at 5. Show that the curve is concave on minus 2 to 0 and then convex from 1 to 3, and then find the coordinates of the point of inflection. Okay, so let's have a look at the function, and then in the first instance we've got to differentiate it twice to find the second derivative and then consider that. So y is equal to x cubed minus 2x squared minus 4x plus 5. For first derivative, dy over dx, find our gradient is 3x squared minus 4x minus 4. When we differentiate it again, d2y over dx squared, we get 6x minus 4. Okay, so as you see, 6x minus 4 is obviously a linear function. Let's consider that on the interval then. So on the interval minus 2, 0, and so when x is equal to minus 2, d2y over dx squared is equal to 6 times minus 2 minus 4, which is equal to minus 12 minus 4 is minus 16, and when x is equal to 0, d2y over dx squared is equal to minus 4. So that means d2y over dx squared is always negative over that interval. It's a linear function. So always negative on the interval minus 2, 0. Well, so what we're saying is d2y over dx squared is always less than or equal to 0, therefore concave. So hit pause, copy these notes down, and then I'm gonna have to wipe them and write down. Well, we're gonna check if it's convex from 1 to 3. Just not got enough space on here. I think I'll change to a blue pen for the next bit. So hit pause, copy this bit down. When you're ready, hit play, and we're gonna check if it's convex, i.e. from 1 to 3, is it going to be greater than or equal to 0? Okay. Right. So we know our second derivative, d2y over dx squared, is equal to 6x minus 4. So on the interval, 1, 3, when x is equal to 1, d2y over dx squared is equal to 6 minus 4, which is equal to 2, and when x is equal to 3, d2y over dx squared is equal to 6 times 3 minus 4, which is 14. So it's always positive. So d2y over dx squared is greater than or equal to 0 on the interval 1, 3. Therefore we have a convex function. or you can write it like that, you can write it as 1 to 3, either. Okay, now we've got to find the coordinates of the points of inflection. So hit pause, copy these down, and we'll move on to section B. Okay, so we know our second derivative, d2y over dx squared is equal to 6x minus 4 at the point of inflection. d2y over dx squared is equal to 0. Therefore 6x minus 4 is equal to 0. 6x is equal to 4. That's adding 4 to both sides, so x is going to be equal to 4 over 6. If we simplify, that means x is equal to 2 over 3. And then to find y at this point, just give myself some room here. Therefore, I'm going to change this time. Therefore, y is equal to, sub it back in the original equation, 2 over 3 cubed plus 2 times 2 over 3 squared minus 4 times 2 over 3 plus 5. Nice, simple. So we got 8 over 27 plus, that's 4, so 8 over 9. That shouldn't be a plus there, that should be minus. Just change that. There we go. Oh, I shouldn't have changed that as well. Right, there we are, that's better. Minus, wow, okay, it's interesting. 8 over 3 plus 5. So if we just have a look at our fractions and see if we're lucky, 8 over 27 minus, multiply both of them by 3, minus 24 over 27 minus, multiply both of them by 9, so 72 over 27 plus 5, we'll come back to the 5, and we've got 8, well, 24 plus 72, it's 96, take away 8, so be minus 88 over 27 plus 5. 5 times 27, what have we got? Sure, this is much better on the calculator, quicker. Be 5, carry 3, 135. So that's 135 minus 88 over 27, which is equal to 135 minus 88. And we have 47 over 27. So our point of inflection is given by x is 2 over 3 and y is 47 over 27. Okay, so hit pause, these are just workings. Copy the solution down. When you're ready, hit play, and I got some classwork for you to get on with. So here's our classwork. Exercise 9L, page 259. I will include this in the assignment. Okay, good luck.